Good day everyone, welcome to 3D Experience 2022 launch online event of Computrends. I am Jayson. I am one of the applications engineer of Computrends who specializes in manufacturing solutions. Our presentation will last less than half an hour, so let's get started. Today I am going to show you some pretty cool functionality regarding surfacing. Not really anything new, but for such much people don't know exists in SOLIDWORKS. A lot of people have thought that SOLIDWORKS is only a solid modeling program, but today I'm going to show you far from that. Over the years, SOLIDWORKS have invested into creating a lot of pretty events functionality regarding surfacing. Let me use this carving knife demo in order to show you that. I'll show the surface modeling capabilities found within SOLIDWORKS. Then you'll see that it's a very powerful tool filled with flexible and intuitive workflows. Let's create the handle. Here's our assembly. It's composed of different components, and notice that it doesn't have a handle yet. I have a sketch available as a reference to create the handle of the carving knife. The SOLIDWORKS UI is known for its ease of use, and a big part of it is due to the context-sensitive toolbar. In this case, I pick on a plane, so SOLIDWORKS recommends starting a sketch on the plane. I'm going to start by inserting a concept sketch. I can scale the picture precisely to size by picking a reference and keying in an exact value for the length. If my picture happens to have transparency such as a PNG file with no background like this file, I can automatically remove that background. Surface features can build up fast, so to stay organized, I can drag features into folders or even create subfolders if needed. I've already created one master sketch for the top view of the sketch, so I'll move on to a side sketch. The most important sketch entity when surface modeling is the spline. You're probably already familiar with how to sketch a traditional spline, but let's review to be sure. Traditional splines are defined by through points that have handles to control direction and magnitude. The fewer points, the easier they are to control. But as you add more, it can get difficult to ensure a perfect transition of curvature across the length of the spline as I highlighted this curvature combs. To make this easier, we've introduced style spline which are defined by a control polygon. I can convert a traditional B-spline into style spline from the right-click menu for better quality curve and simpler parametric control. The control polygon make an inflection point like this very noticeable and easy to fix by dragging the construction geometry into place. I could optionally fully define the spline by adding dimensions and constraint to the construction geometry. Let me finish the sketch by tracing the image reference. Then notice how easily to control the shape of the spline. Fast forward, I can jump to the complete sketch. These two sketches are considered master sketch because they'll drive all the downstream features we'll be creating. Since I'll be keeping them visible during for the modeling process, I can change their color to a light gray, and to make them easy to access, I can add them to my favorite folders. This places them at the top of the feature tree so they never get buried by the rest of the features I'll be creating. Again, with the help of the intelligent context toolbar, creating a new plane is only a couple of clicks. No searching through drop-down menus to find the tool I'm looking for. To create the sketch for the front of this carving knife, I'll use another style spline. I'll take the time to make sure it is the right shape and size by adding horizontal and vertical relations to ensure a smooth transition from right to left when these roof faces eventually gets mirrored. To control the width of this front face, I can draw a vertical construction line that references a point on a previous sketch and then make the spline tangent to it. Notice how the recommended relations adjust to the selections I'm making. I can also add coincident relations to the masker sketches to ensure it's the perfect height. Now, I can create our first surface feature, a planar surface, the easiest of all features. Next, we'll need to create some features that reference to the curves we already sketched in the master sketch. We could reference them directly, but I prefer creating unique sketches that are driven by the master sketches via the convert entities command. I'll repeat this process to create a total of 3 curves, but only need 2 curves to create the top surface of this model. So I'll use the project curve feature to combine 2 of the curves into one. Project curve allows me to parametrically create a 3D curve out of 2 2D curves, something a lot easier for me to conceptualize and generate from my hand sketches. Fast forward, I've converted a few more curves. Now I need to convert a 3D curve so I can use just a portion of it. I can do this in a 3D sketch. Notice how none of these downstream sketches need any dimensions because they're all geometrically constrained to the master sketches. This will make future design changes simple and predictable. Let's get back to the making surfaces. I'll start with a surface sweep. I can select the straight line as the profile of the chamfered surface and choose the 3D as the path. To expand the width of the surface as it progresses upwards, I can reference the model edge of the planar surface as a guide curve. Another way I can accomplish a similar surface is with the boundary surface feature, one of the most versatile surface features. I can choose 2 3D curves as the boundaries, and rather than trimming the curves like I had for, I can visually drag the connections point on the preview to wherever I think they look best. This is quick and easy and can be edited at any time. I can repeat this process for the side chamfered surface and then move on to the top surface with another boundary surface feature. This time, I apply normal to profile boundary condition to ensure the surface blends perfectly across mirror plane. To fill the 6-sided void between the 3 chamfered surfaces, I need a curve to fully enclose the open edges. I do so by converting sketch entities into a new 3D sketch. To shorten the curve to the extent of the surrounding surfaces, it's as simple as dragging and dropping the endpoints. Filling a 6-sided surface can be challenging in a parametric surfacing modeler because NURB surfaces prefer to have 4 sideds to predictably define the direction on the UV curves. But this is no challenge for our field surface feature. By selecting any combination of model edges and sketches entities, SOLIDWORKS patches the gap with a perfectly smooth surface. To ensure I have no visible edge between the surface and the surrounding chamfered surfaces, I can adjust the boundary condition of those edges to be tangent. I can also merge the result to stitch them together into a singular surface body, all in one command. I'll check the quality of the resulting blend by activating zebra stripes. This ensures a buttery, smooth transition around all the edges with no signs of abrupt curvature changes. This is exactly what we need for the highest quality of consumer product design. To create the bottom surface, I'm going to start by trimming the bottom curve to a couple of horizontal and tangent lines, as I'll be rounding off each open end with separate surface features. Extruding this edge allows me to create a reference surface. I also need a reference plane offset from the right plane. And that as simple as control dragging it, so I'll add a pierce relation. Clicking a vertex from my reference surface automatically defines the offset distance of the plane. I'm going to use another surface sweep to create this bottom section because I want to carefully control the angle it meets the chamfered surface, so I need a profile sketch. I want to ensure the profile stay properly oriented to the surrounding geometry throughout the entire length of the sweep. This positions the vertex at the exact point where the curve intersects the sketch plane and maintains this relation through the entire length of the curve. This will allow me to control the angular deviation between this bottom surface and the chamfered surface above with a level of precision. I can visually experiment with the value of the angle by dragging this slider on the dimensions dialog box. When I'm satisfied with how it looks, I can key in an exact value. Choosing the bottom edge of the chamfered surface as the path by selecting even more edge by the surrounding surfaces as guide curves, I can obtain complete control over this final shape. By showing the master side sketch, I can quickly convert a curve to use for another reference surface that runs across the entire length of the carving knife. To patch up the back end of this model, I can try using a boundary surface by notice how the UV curves are transposed across the surface preview. This may be an acceptable result in some scenarios, but since we're planning on shelling this out and adding features for manufacturing, it's best to avoid the converging UV curves created in this 3D-sided scenario. As an alternative solution, I can use the field surface command to make a non-converging mesh pass through the boundaries while respecting to the unique conditions that are assigned to each edge. That is exactly what I was looking for. I can use another field surface to patch the front end of the sweep surface. Since I'll no longer need those reference surfaces, I'll delete them to clean up my design. After mirroring the surface bodies, I can knit them together, and as long as the result volume is watertight, I can convert it into a solid body. I'm going to check my progress and make sure I have a clean parting line, and I want to check the aesthetic and ergonomics across the vertical direction with the draft analysis. There's some positive draft on the bottom surface I have to remove. To find the sketch and the dimension I need to edit, I simply click on the area of concern and be presented with a breadcrumb trail or related features. From there, I can find the sketch I'm looking for. Just by clicking the sketch, the angle dimensions is displayed, allowing me to drag it to a new value by snapping to the on-screen protractor. In seconds, I've resolved the issue and my design is looking pretty good so far. Let's create the trigger. Currently, the profile sketch of the sweep also defines one of the boundaries of the field surfaces. To edit the sweep independently, I have to separate them from one another. I'll start by copying the profile sketch, and I can paste it to the same plane to duplicate it and create an extruded references surface so I can connect the field surface to it. Now, the field surface is completely independent on the changes I am about to make to the sweep surface. Since I'm not certain about the modification I'm going to make, and I can create, sketch a new spline to preserve the original spline. Once it properly matches my HUD sketch, I can choose to replace the original spline with a new one. Moving forward, this is an ideal workflow to ensure all the downstream features now reference the new spline and rebuild perfectly. Before blending the two surfaces together with a smooth transition, I need to trim them back to add a gap between them. I can do this quickly with a very simple 2D sketch. The boundary surface feature is great for blending one surface into another. Both boundary conditions can be set to curvature continuous for the highest degree of curvature continuity. Like a spline, you can adjust the magnitude at either edge to change its magnitude of influence. Despite tweaking the magnitude, I can get the resultant boundary surface to perfectly match the hand sketch. Instead, I'll need to make a change to the underlying sketch. By showing the sketch, I can grab a vertex and drag it to a new position. The feature is rebuilt immediately, making it a perfect workflow through design changes during a design review. It doesn't take long to find the perfect position. Using a similar technique, I can create a thumb indent on top of this handle. Using two splines to trim this area away leaves me with two separate model edges at the base of indentation. This will allow me to extend just a portion of the flat edge at the bottom. When extending a surface, the same surface option nearly recreates the original surface by interpolating the UV curves, and the linear extension is used to produce a flatter result, which is exactly what I need. Now, I can enclose this boundary with a sketch of a line connecting the two open edges. The boundary surface can be used with a wide variety of sketch, edge, and boundary condition in multiple directions to produce a perfect surface. Once again, changes can be made to the underlying sketch to obtain the exact aesthetic I'm looking for. Let's roll to the rollback bar down to the end of the feature tree to see how the rest of the feature updated. Expectedly, I'll need to add some of the new surfaces to the neat surface, but the rest updates with ease. As a finishing touch, I can add a few fillet from the context bar. Looks great, but no design is completely without a design change. Let's edit one of the master sketches and put our modeling practices to the test. Once again, just like editing any of the previous features, I can modify the entire design by dragging any of the entities in the master sketch to a new position. In seconds, the model rebuilds flawlessly. This is a testament to our master sketch workflow and the reliability and predictability of the SOLIDWORKS surface environment. This is the result after placing the handle we made. So that's it. So I think we're done. I hope this demonstration helps your design surface modeling process. Again, thank you so much for participating on our event.